Hi guys, thanks for joining. So, as Sarah has already told, we have already explained like decision trees earlier, but I will be like explaining you in general what is decision tree, and along with that, I will be also explaining you like what are ensemble methods and how and what are the algorithms there in ensemble methods. So first, what is decision tree? So as you can see here, decision tree is something like a tree structured algorithm. So based upon the features you choose, you make a decision in such a way that you divide the uh, whole data into particular like classes. So decision tree is like a foundational supervised learning algorithm. So it is used for both the classification and regression. So classification is like you want to do like spam detection, or you want to find out whether the patient has obesity or not, depending upon the data provided in a healthcare setting. For example, uh, if the patient has cancer or not. So that is like classification, right? So you want to classify based upon the data. So you can use decision tree for that. Along with that, you can also use for regression. For example, in order to predict the weather, in order to predict the stock price, or in order to predict any kind of like rainfall prediction or anything, so you can use this is called that is called regression task. So you can use for both tasks, for classification and regression. So this is like the powerful this is the base foundation for the ensemble methods. Ensemble method is like combining multiple decision trees, or like forming new algorithm based upon the decision tree. So this is like the base uh, model which is used for later different algorithms as well. So as you can see in the image here, so what's happening over here, say is there is a data of an patient. So whether he gets a heart attack or not, like, so the data, as you can see here, there is a age column. As you have seen yesterday, there are like different columns uh, for the health record, like not health, not yesterday, but I am saying in general, you have a patient's data. So where they have like age, weight, smoke, or like different columns of the data for each particular individual, and you want to find out whether the patient is will like has an heart attack or not. I mean, you want to understand the risk of preventing a heart attack. So for example, in order to use decision trees, what happens, for example, if you can see here, there is a age column. So based upon the age column, if he is less than 18, you divide it into one kind of uh, portion, and if it's greater than age 30, you divide it into other side. So based upon the age, we have divided it into three different columns. Okay, so and what happens after dividing the data, so you will find out that, for example, like in a typical scenario, you will find out that what happens, 18 to 25 are like low risk based upon the data. Okay, if the age is like below 18, so you again divide based upon the weight. If he is below 18 and his weight is above 60 kgs, like it means like he may be obese. Okay, he might have like high risk of getting a heart attack. Okay, so in that way, there is like one more column called smoke. If he is greater than 30 and if he smokes, then there is a high risk of getting a heart attack. Like this is like a simple decision tree. If you can see here, so this the first one is called root node. So the middle ones where we have like weight and smoke, these are called uh, so the last ones are called leaf nodes. Okay, so the other ones are called decision nodes. The earlier one also is also called a decision node, but this is also called as a root node. The root node is like where the maximum split happens. For example, if we have like three different columns, if we have like 100 different patients, and based upon only one, like based upon age column, you were able to split like maximum uh, patients into two different columns where they're like where there's a risk of them getting a heart attack or not. So based upon that, you subdivide the tree. So at first you divide the tree using age, because with the age, for example, in this, for this data set, you were able to identify the low risk, like all of the people who are from 18 to 30 are like low risk. So then you have used age. So in order to find out which feature is important and which feature to use, like which feature to split, so there are like different criteria. So one is called Gini impurity, and other is called entropy. These are like math concepts where you use, there is a formula, how do you split the decision tree. Okay, so this simply what I would be saying is like this gives a number in such a way that if you compare like three to four different features, whichever feature does best in this formula is used for dividing the tree. This is like simple intuition. So here what happens in decision tree, you split the data in such a way that you want to classify the overall patients. Okay, so this is like, in general, the decision tree works with root node. So root node is like the top node, represents the entire data set, and split is based on the feature that provides the most significant information gain or impurity reduction. Okay, so and the splitting criteria is like, as I have told you, Gini impurity. What I would be saying, like Gini impurity is measures how often a randomly chosen element, like if you choose one uh, custom and patient data, so it explains a randomly chosen patient data how would be classified, like it is, are they classified correct or not. So the our goal is to minimize the Gini impurity. So our, if we decrease the impurity, what happens is like we split the data well in terms of random, for like in a decision tree. Okay, so what, so the splitting happens for all the different features in the data set. Along with that, all the data points are like, so how do you stop the criteria? Either how do you stop the splitting? Either all the data points are classified correctly, or there is a criteria met. For example, there are like different hyperparameters. What I would be saying hyperparameters, like, so you can also come up with like what is the maximum depth of the tree. So you can choose at first. So what is the minimum samples per leaf? Like if you can see here, this is a leaf. This is one more leaf. So you want to split in such a way that the low risk candidates, like minimum, you can come up with a minimum split length, like minimum split of the patients. Okay, so in that way you come up with the decision trees. So but what happens when you take a data like a, like data of like 100 patients data and you develop a decision tree? So what happens, all the data is divided into different classes. But what happens in general, that model has like some strengths and weaknesses. Okay, so what do I mean by that? For example, if you take only one decision tree, so you are taking a data and you have developed a decision tree, and that model is like in general does well on the training data. But what happens over the time, the eating patterns of the customers changes, or due to the weather and due to the smoking of like a lot of people smoking more in terms of age 18 to for example 18 to 30, they do also get like heart attacks. So the data pattern changes, right, on a regular basis. So this model which we have developed doesn't work. So what happens? This is called overfitting. So the tree tends to become more complex, like perfectly. It only fits on the training data, but if you see the testing data or like in general over the time, the data pattern changes. The patient's records also changes. So this is the so in the what happens is the overfitting happens. So in order to work with this kind of data, you have to either retrain the model or you have to come up with different methods. Okay. So in general, decision tree works well, but in order to work even better, you come up with like multiple decision trees. So there is a concept called generalizing the machine learning models. So what is generalizing machine learning models? So generalizing machine learning models is like you come up with a machine learning model which not only solves the problem at present but also does well on the unseen data. For example, if you can see here, there are like two concepts you need to understand. One is underfitting and overfitting. For example, if you can see here the image, so this is a 2D plot. For example, if you can think of, there are only two features. Okay, so and with these two features, for example, there is a feature called uh, age, and there is a feature called weight. Okay, and you want to develop a model based upon those two features, whether they have like cancer or not. Simple. Okay, not cancer but obese. So what you can do is you develop a model. So you developed a model and that model splitted the data in such a way. Here, if you can see the first image, the data is splitted with a straight line. So what happens here? The model is not doing well because some of the points here. For example, if you can see here, X is like they don't have obese. This zero symbol is like they have obese. But if the model, as you can see here, it has not splitted well. Some of the patients who has obese are shown in not obese, and some of the patients not obese are shown in obese. Okay, so this is like underfitting. The model has not fitted well on the data, so it has underfitted. For example, if you see the last image, okay, so the last image, the model is too complex and it has fitted very well on the training data. So what I would be saying is like the model like generalized well on the particular scene data, what the training data. So it has fitted everything perfectly. So if you can see here, whoever doesn't has obese as on this side, on the other side of the model line, and whoever has obese as on the other side of the model line. This is also not good, like in general, because when you come up with this kind of data, overfitted data, overfitted model, in future you come up with a data point, it's here, for example. But what happened, the data pattern changes, the eating pattern changes and everything, so the model doesn't do well on the future data. So what I would be saying is you have to come up with a model which is like not overfitted, which is not underfitted. Okay, it has to do well, it has to generalize well. So it has to learn the patterns in the data in such a way that it should come up with a model in this way. So it has to split in such a manner. So here the error will be there, but the error is like minimal. Here if you can see here, the error is like more. There are like lot of data points which are on the either side of the model. if you take like 100 patients, here the error is around 70 on the first one. So on the last one, the error is around 0. But you have to come up with a model where the error should be minimum and the error should be like around 80, like the accuracy should be around 95, and it has to do well. So this is called underfitting and overfitting. So you have to develop a model in such a way that the model should not be underfitted and the model should not be overfitted. So as I have told you, the underfitted model has like high error in terms of training error. So if you can see here, there is a one more diagram. So this is called, you have to understand one more concept called bias and variance. So what is bias and variance? As I have told you, so if this is like one more image which is used. So here the data points are like this. So this is one more example. So the data points are like this. So you have come up with a model as a straight line. If you want to, this image is for the house price detection. So you know the size of the house and you want to predict the price of the house. Okay, for example, if you see here, the size of the house is here and the price of the house is here, but the model shows for this size the price is this much. Okay, if you can see the plot, if you see at the last, the size of the house is here and the price of the house is this. Okay, it has over like fitted very well. But what happens in future, there will be a size of the house here, like one data point, you come up with this size over here. Okay, if you can see the arrow, but what will be the price here? The price will be here, but for this size the price from the line is here. So it is not doing well. So like the error will be maximum. So while training we have more error and the model has not done well. So it is called like high training error. Where we have high training error, it is called an high biased model. So training error refers to bias. Okay, when we have like high testing error, during testing we come up with error. Like this is the model which we developed on the training data, but the testing data is somewhere not near the training data. What happens for the testing data on an overfitted model? The testing error will be low, but the training error will be high. Like not training error will be low and the testing error will be high. Okay, so this is called high variance. So what I am saying is like overfitting is also called as high variance and underfitting is also called as high bias. So you have to come up with a model which is like good fitting, which has low bias and low variance. So in order to come up with these kind of models, what you can do is like there are like this is called ensemble method. So ensemble method, there are like two different ways. There are two different techniques you can do. Major like there are like many methods. There is like bagging, boosting, and there is also one more method called um, that's not most important, but one more method. Let me recollect. Yeah, I could not able to recollect right now, but if I recollect, I will tell you. But these are like two most important ones: bagging and boosting. So what happens here? So this ensemble is like ensemble. The meaning itself explains you combining multiple models. Okay, so in an ensemble method, if you can see here, you have a data set. So what you do is like you divide data into different subsets of data. Different subset of data means, for example, if you see the data here, there are like 100 samples, for example. So you divide data in such a way that you come up with each data set of 40 samples. Okay, you can come up with like any number of samples. It can be 10. So here there are like 40 different samples. Okay, some of the samples from the first data set, and then some of the unseen samples from the data set. Okay, some of the samples from the first and second data set, and some of the new samples from the 100 samples. So you can come up like 20 different data sets from the original data, and you develop 20 different models. So all of them are decision trees. Okay, and you combine those 20 different samples um, and general answers, and you come up with the best performing like model. For example, if you are working on a classification, so there are like obese, as I have told you, you want to find out whether a patient is obese or not. So you have like 100 patients. Right now you want to come up with a data point such that there are like 40 different data points. There is like 40 different patients and 40 more different patients. For the first data sample, depending upon, you tested a new sample on this developed model. This is a developed model. So you get answer as obese. For the next, with the new model, there is, for the second model you get obese. For the third model you won't get obese. So here what's happening, you, for classification, what you will be doing is you will be using majority voting. So majority of, if the majority of the models says if he is obese, then you choose like obese. If the majority of the model says he's not obese, then it will be not obese. See, this is like parallel learning. So you are dividing the data into different data sets, and then you are developing a model, like different model, like multiple models, and you do majority voting. This is for classification. So one more method, it is called boosting. So what happens here is like you take a sample of data and you develop a weak model. You develop one model. So what you would be doing is you take this model and you train this model on the new data set. So what happens? This model will improve its capabilities. Okay, so you come up with a one more model which is better than the previous one, and you train again this model on the new data set. So what happens? This weak learner will like will improve. So this is like sequentially learning the old model. So what you would be doing here is, so you will give weightage in such a way that the weakest model will have less weight and the strongest model will have more weight, and you take all of the models and then you come up with a solution. So this is like boosting. So as I have told you, one more method is called stacking. So that is not mostly used anywhere, but these are like the bagging and boosting. So as I have told you, how do you do bagging? First step, in order to do bagging, you have to bootstrap these samples of the data. For example, there are like 100 samples. So you create multiple subsets with replacement. So what I would be saying is replacement is like, first you choose a sample from the 100 samples and you put it in one table. And from the 100 again you choose one. From the 100 again you choose one. But it doesn't decrease. Like if I choose one sample from the original 100 data points, so it won't decrease. Like you are using with replacement. Like you can choose again also. For example, from the 40, from the first subset, there are like 40 different samples, right? So one patient data can be come up like any number of times. It doesn't matter. So what we are doing is like you are coming up with different samples of subsets of data. Okay. Then you come up with different subsets of data. Then you train a model. So if you are doing classification, you will be using max voting. Okay, max voting. So you will be voting for this. For this model has given he has obese. The second model has given he has obese, but the third model has given he is not obese. So you are doing like whatever is the maximum. The maximum is like obese 2/3, right? So you will end up saying that this new candidate has obese. For example, if you are using for regression, so first model, if you are predicting the house price, first model has told that the house price is around 100K. The second model has told the house price is 105K. The third model has told the house price is 108K. So you would be doing average of that 105 plus 108 plus something 110, for example. So you average those and you come up with like 105.66K. So that is for regression. It it's simple to understand. So what in, you come up with the different subsets of data, you train a model depending upon the use case. If you are doing classification, you choose max voting. If you are doing regression, you just average the answers and then you come up with the final answer. So in boosting, so what happens in boosting, you train a model. That's called bagging, right? So bagging, in everything you use decision tree, like ran a decision tree. So in boosting, you train a model, then you take one more data, like one more subset of data, then you improve the capabilities of the old model. Okay. So in you do multiple times, you come up with a final model, then you assign weightage to different models such that the first model will have less weightage, the last model will have more weightage. Then you combine all of these solutions, then you aggregate. If you are doing classification, same thing. You do max voting for classification, and regression you do average vote, like averaging. That's called boosting. So here, like which you want to know, like when we use bagging and when we use boosting. For example, initially you have developed a model with like simple logistic regression or decision tree. The decision tree is like one decision tree, right? One tree. So your goal is to reduce. You have seen that your data has like variance. Variance is like your model has best like overfitted in general. Okay. So the what I mean is overfitting is like you have like less training data, but you have more testing data, like less training error. You have more testing error. So there, your goal is to reduce variance. Your goal is to make the overfitted model to best fitted model. Like so, there you use bagging. Whereas your goal is to increase the model capabilities. Like the model has doesn't generalized well. The training error is high and the testing error is high. Then you use boosting. So coming in terms of bagging, random forest is an example of bagging algorithm. So decision trees. So the decision tree is like there is a tree. So what is random forest? In a forest, there are like different trees, right? Multiple trees. Okay. So random forest is you are coming up with random different trees. So that is the name. It has got random forest. Okay, so you come up with the different decision trees, and then you use those different trees decision. Ultimately it is called random forest. Whereas boosting algorithms, you generally boost the algorithm, like you are increasing the capabilities by providing more data and increasing the capabilities of the old model. So coming in terms of boosting, there are like different boosting algorithms like ADA boost, XGBoost, light boost, cat boost. So these are like different boosting algorithms. So boosting algorithms, there are like different boosting algorithms. So depending upon the use case, you work with the boosting algorithm. So in general, most of the boosting algorithms, like mostly we use XGBoost. XGBoost is like extreme boosting algorithm. Okay. So what do I mean by extreme gradient boosting algorithm? Okay. So XGBoost uses different features. Like there is a technique called not regularization. So we will be explaining regularization in next classes. We will be explaining you what is regularization and what are the concepts behind regularization. So what I would be saying is XGBoost along with the weak learners, along with using decision trees. So there are also different 2 to 3 different concepts incorporated into one algorithm. So there are like L1 and L2 norm. So what it does is XGBoost not only uses decision trees or not only uses boosting, it also uses concepts called regularization. So it does generalize well. When you choose XGBoost, the model performs even better compared to normal boosting algorithms. So XGBoost, as I told you, it has like regularization concept, and if like missing values. Until yesterday, we for example, if we have done like a logistic regression, we have to deal with missing values, right? If you have like categorical values, not categorical values, if we have like data which is like not normalized or standardized, what you have to do, you have to come up with the data in such a way that you want to uh, convert them into, like you want to standardize or normalize the data. Whereas XGBoost, you doesn't need to do anything, like it handles itself, because the algorithm is powerful in such a way that if you have missing values also, you can train the model. Along with that, normalization and standardization, if you don't want to do normalization and standardization, it does well. But what my advice is like, in order to perform even better, you have to handle the missing values, you have to do normalization standardization, and if you again use XGBoost, it not only does well on the training data, in future data, like in future if you like production data, like new data, it does well compared to earlier models, because this inherently understands the patterns on the data very well compared to other models. So what are the practical use cases of different models? For example, I would be explaining you like where we can use uh, decision trees, like bagging and boosting algorithms. Okay. For example, if you are in a healthcare industry, as I already told you, if you want to classify patients based on symptoms and you want to test the results, like you want to predict the likelihood of diseases based on the patient's history, so there you can use decision trees. If you want to come up with a complex model, you can use bagging or boosting. Okay. And in finance, for example, if you want to determine if a loan applicant is a credit on the based of the credit risk, like if you have like financial data and you want to determine whether this candidate, based upon the credit data, whether he gets loan or not. Okay, there you can use this. Or else if you want to like find out the suspicious activities or fraudulent activities of the transactional data in a banking industry or anomaly detection, so there you can use these algorithms. So if you are working in a retail or e-commerce company, there you want to classify customers in such a way that similar kind of customers are classified into one bucket, like one group, and based upon the group you can do marketing or sales. You can give offers for those particular customer segment. There you can use there you can use these algorithms. Or you want to suggest based upon their past behavior, like if they have purchased similar kind of products, then there also you can choose like deploy this kind of models. If you are working in a manufacturing industry, for example, there is a mission, there are like different missions, right? So for the missions we have like different uh, sensors inbuilt, incorporated into the missions. So with those sensors we extract the data, how the mission is being performed, like is doing. And based on the extracted features, you can develop a model and you can check whether the mission will fail in future in next 30 days or next 50 days. And you want to check the quality of the device. So there you can use these models. So these models are like used in like many industries. So as I have told you, these are like simple, as I've explained you in general. But if you are interested in learning though all of these topics, you can deep dive. And there are like different hyperparameters you can choose to tune the model in order to do better. So this is like an iterative process. First you develop a model, then you check what kind of issue it is facing. Then based upon the issue, you choose one more model or you choose like better performing model, and then you test that in real world scenario. And if it is also doing well on the real world scenario, and then you deploy on an like deploy wholly into your system. Okay, so XGBoost was developed around like 2013 or 2014. So it is like on like 10 to 12 years old model, not more than that. But most of the like Kaggle competitions, most of the industry use cases, anywhere you see, XGBoost is the winner compared to any other models. So there are like some courses there are like some courses out there in the market only teaches you XGBoost. Okay, it is such a powerful model, and there are like different in-depth intuitions how do you can come up with a model depending upon your use case, and you can deploy in production. Yeah, thank you. So this is like a explanation of bagging boosting, how you can come up with better performing models with the same kind of data. So when you have like data, like you don't have like much features, like much data, so there also you will use these algorithms. So next class, Lakshmi Narayana will explain you with an example of a random forest, where he has developed a model with the random forest, and he will explain you in detail the code snippet for the random forest. Thank you.
Thank you for watching. Please like, share and subscribe to KKR Gen AI Innovations channel.